Okay, hi everyone. So welcome to my talk, which is called Beyond Your First NIF. So I'm not going to go too much over NIF basics, but just as a quick recap, what is a NIF? It's a function written in a native language that gets dynamically linked into the beam. A NIF has a lot of nice properties, like it can leak memory, it can hog the schedulers, it can crash the beam. Then you could ask, why should I want to do that? The usual reasons are that you need raw speed, or you need to reuse existing libraries, usually C libraries, Rust libraries, whatever, or you need low-level system access. There are other ways to obtain that, but NIF is one of them. Usually, your first NIF looks like this. So it's a NIF that just gets two integers as input and sums them. And today we're going to go a little beyond that, and we're going to explore what else the NIF library offers us. So we are going to cover data exchange between NIFs and the beam. We're going to try to write NIFs that don't block the scheduler. We're going to go over NIF resources and debugging faulty NIFs, and then we're going to quickly see a bunch of language choices in which you can write your NIF. So for the examples, I used C, so warning, C ahead. All the examples will be available on GitHub, so don't sweat in like understanding C, because it's not possible quickly, because we also have less time. And it's not as nice as Elixir to read, but that's what you had to deal with. So quick introduction for myself. I'm Riccardo Binetti. You can find me online as Arbino. I'm a senior backend engineer at Remote, and I've been using Elixir as main language since 2017. Recently, I've been messing with NIFs for my Tiger Beetle Elixir client, so that's why I went down this rabbit hole. So let's start with some basic data exchange. The basic NIF signature looks like this. So you can see that we are accepting an array of NIF terms, and we are returning an NIF term. So everything that goes between the Elixir or Erlang word and the NIF word has to have an NIF term type. So first of all, we need a way to convert this from and our native C types. To do so, the NIF library provides us with functions to extract terms. So we have all the NIF get and NIF inspect functions that allow to pass in a term and populate a native type, a native variable on the C side. This is what they look like. So here, for example, we are extracting an integer term. We just declare a variable, and we call NIF get int. So this can return an error if for example, if the term is not an integer. But once we extract that, then we can use foo below, and it has the same value as the term that came from the Elixir word. Of course, the beam is dynamic, so we might have a NIF function that accepts an integer or a float or something else, while on the C side, we're statically typed. So we need to have a way to switch on term types. And to do that, we use either NIF term type or NIF is integer, NIF is float, whatever. So the idea here is that you have separate code paths on your C side to handle the different types. So for example, if you use NIF term type, you can switch. It returns an enum that tells you what is the actual type that is contained inside the term, and you can have dedicated case clause to handle that. As a last step, when we return data from a NIF or send it as a message, we have to convert it to an NIF term. To do so, we can use the NIF make functions, which basically accept an integer, a float, or whatever, and return an NIF term. For example, here we are creating a tuple. We have a NIF make atom, which creates an atom with the value answer. We create a value for an integer, and then we use NIF make tuple to return a tag tuple that contains the values we indicated there. Here is a couple more useful patterns that you might use in your NIF. So here is how you iterate through a list. There is this function called NIF getListCell, and basically it looks, if you squint hard enough, it looks like a reduce. So basically each time you enter the loop, you populate your head, and you do something with your head term, and then at the end of the loop, you assign the tail to the rest of the list. And so you go on, and NIF getListCell returns 0 when the tail is empty. Here is how you build an Elixir struct. So as you probably know, an Elixir struct is just a map with a special key. So what you can do here is that you can, if you have an Elixir struct on the Elixir side, you create your keys and values arrays. And you have to be careful to populate the struct key with the name of the struct. And note that you have to add the Elixir prefix because that is basically implicit when dealing with Elixir aliases. But since here we are dealing more with the Erlang side, we have to add it and manually. And then after you've done that, you call NIF make map from arrays, and you return your map. So this is the basic of how you deal with data between a NIF and Elixir. Now, there is a piece that if we go back to the signature that we ignored right now, but it appeared basically in every function call, and it's that env variable. So that env variable is of type Earl inif env, and it's very important because the environment is the place where all the terms live. And so all terms of type Earl inif term belong to an environment of type Earl inif env. And most importantly, the lifetime of a term is controlled by the one of its environment object. So this means that you have to be very careful when interacting between a term and its environment. There are actually 3 different types of environment. There are process-bound environment, which is the one that gets passed as first argument in our NIF calls, so the env that you saw before. There is a callback environment, which is very similar, but instead of being passed in NIFs, it's passed in the callbacks we use when loading our NIF that we are going to see later. And then the third type is the process-independent environment, which is something that we can create manually. So the important distinctions here, is that the first 2 are function scoped. So you receive the environment at the beginning, but then when the function terminates, that environment is not valid anymore. While the process-independent environment is the only one that can be created and destroyed at some point in the future, independently from the scope where it got created. So this is very important and a big foot gun when you want to persist a term that belongs to a process-bound environment or a callback environment outside its function scope. So what you don't have to do, and I've done it many times, so then I learned to not do it, is, for example, create some term with the process-bound environment, and then store that term in some kind of long-term storage. If you're doing so to match a reference between a request and a reply, you can return the reference here, and it will be perfectly valid because it's valid in the context of the process creating it. But when the NIF returns, long-term storage.myref is invalid. So if you try to access it later, it will, I don't know, do something bad probably. So what you have to do instead is, if you want to do something similar, you still create your ref in the context of the process-bound environment. But then if you want to persist it, you have to create another environment, which is now a process-independent environment, and call inif make copy, which creates another term, that lives inside the environment passes the first argument. So in my ref, you have the same reference. So if you look at it from the Elixir side, it looks the same. The big difference is that it lives in another environment, which means that you can then persist both the environment and the reference in some long-term storage, and it will remain valid even after we are out of this function. It will remain valid as long as we don't invalidate the process-bounded, this process-independent environment. Another big gotcha here is that when you use inspect function, so NIF inspect binary and NIF inspect IOList as binary, they're used to take a binary term and basically populate a buffer and a length, which is an early NIF binary. Another foot gun that hit me numerous times when I was fiddling with it is that you don't have to free the binary. So this should make you think. The reason why you don't have to free the binary is that the binary itself has their lifetime tied to the environment. So if you extract a binary, you can't persist it. You still have to copy the term and then extract it with a separate environment to make sure that the binary is still valid. So the main takeaway from all of this is please consider the environment before persisting your term. And now, let me drink a little bit, and then we go through NIF scheduling. So, as you might remember from the great talk from yesterday, this is a high-level view of how processes in the Beam work. If you want more details, again, the talk yesterday was much better at explaining this, but basically you have one scheduler per CPU core, and it executes one process at a time. So here you can see the small boxes, and each of one is a process, and it's getting executed on a scheduler. Now, the big difference between Erlang processes and NIFs is that Erlang processes use preemptive scheduling. NIFs use cooperative scheduling. What this means concretely is that the scheduler, for Elixir processes, the scheduler is able to kick them out when their time is up. But with NIFs, it can't do so. So it has to rely on the NIF being nice and say, oh, please, go, go. And this sometimes doesn't happen. So what is a good, a good citizen, a good NIF citizen do? How much time does it take on a scheduler? The Erlang documentation mentions a suggested NIF runtime of about 1 millisecond. So your NIF, once you enter in the C section of your NIF, should return in some way to the caller in about 1 millisecond. If it takes more, then things start to get problematic on the scheduler side. And so we are going to see a particularly bad example of this. So this is a bad sleep function. It basically implements the same interface as timer.sleep, but the difference is that it sleeps directly on the C side for a certain amount of milliseconds. In the real world, of course, instead of sleeping, you would do some actual work. So let's see what happens when this gets executed on the Beam. And to do so, we will artificially reduce the number of schedulers to 1, so the effect is more clear. And you can do it at startup with the line above, or you can also do it at runtime with the line below. So let's see here a quick demo. So we are going to reduce the number of schedulers here, and this is the normal timer.sleep. So here we spawn a process that sleeps for just 3 seconds and then prints something. And then outside that process, we print some other thing. With the normal timer.sleep, we get the first print. Whoa. And then we get the slept print after 3 seconds. Now, let's see what happens if we use our bad sleep. So let's focus here. both got printed after 3 seconds. Because what happens is that we just had one scheduler, and the NIF process was hugging it up. So it was just staying there and sleeping with their arms crossed, and the other process couldn't get executed there. So the question here is, how do we make our NIF a good business citizen? So there are 3 possible techniques. First one is dirty NIFs. So basically, you use dedicated schedulers to avoid disruption. So the previous diagram I showed you was, I lied a little. So this is the more similar to the actual situation. So additionally to the scheduler, you also have a dirty CPU scheduler for each CPU core, and then you have an additional number of dirty I/O schedulers, which is by default is 10. Note that when you change the number of schedulers like we did before, the number of dirty CPU schedulers changes, but not the number of dirty I/O schedulers, because they are thought to be independent from the actual number of CPUs. So what we can do to make our NIF nicer is statically telling that it's a dirty NIF, and we can do that in the array where we declare all our NIF. We can pass the flag earlnif dirty job CPU bound or IO bound, and it will then execute on dirty schedulers. So how do you choose between, how do you determine if a NIF is a dirty CPU or dirty IO? So basically, it's dirty CPU if your fans go brrr, and it's dirty I/O if it's just passively waiting for someone else, like network, disk, or time, or whatever. And the nice thing is that we will see in the next technique that you can actually dynamically switch between the two. So there we define it statically, but you can also switch dynamically between the 2 dirty schedulers. So the second technique is yielding NIFs. In this case, what we do is that we split work in small chunks. So here, basically, instead of sleeping for the number of milliseconds, we read how many milliseconds are remaining, and we decrease the count, and we say, okay, are we done here? If we still have to sleep, we sleep just for a single millisecond, which is more or less the amount that we are allowed to. And then what we do is that we serialize our state, which is in this case just the number of remaining milliseconds, and we tell the scheduler, okay, please call this function at some point in the future with these arguments. So basically, at the beginning, you will get the new remaining count and start over like this. If we're actually done, we just return OK. And notice that this, if you squint hard enough, this kind of looks like handle continue. So you do your job one piece at a time. And the flags variable is where you can actually dynamically switch your dirty type. So if you pass here earlnif dirty job CPU bound, then the NIF will be scheduled to a dirty scheduler the next time it runs. So of course, the hard part of yielding NIFs is that they are basically stateless, and so you have to be able to serialize the entire state of execution inside an array of terms, because the next time you're going to be called, you're just going to be able to look at that and say, okay, I arrived here, let's resume from there. And in real world, in real yielding NIF, where you don't have a time-dependent payload that you can just say, okay, I spent 1 millisecond, you also have to call this env consume time slice function. Basically, what this does is that you guesstimate the percentage of a time slice you spent already in your yielding NIF. And so you basically have to try it out and see how much time your NIF takes. And you say, okay, I did 5% of my time slice, I did 10%. And the scheduler at some point will return okay, stop here, please yield, and you will have to yield at some point. Notice that it's still the NIF responsibility to be truthful about how much of the percentage of the time slice it's spent, so the bean still trusts you to estimate progress correctly. How do you do it? You have to try things out and measure things. So the third technique is threaded NIFs. So you basically run your code in a dedicated thread, and then you can send a message back. Here comes some chunky C. So I'll try to focus on what the main parts are doing. So here we retrieve the self PID of the current process. We create a reference because now we're doing message passing. So we want to match the request with the reply. So then the thing you do usually is that you create a reference and match it when you receive the message. Then, as mentioned before, we allocate a process-independent environment because we want to store the reference in the thread because it needs to send them to match them. Then we allocate some thread data, so all the data that the thread needs to do its job. And then we create the thread, passing in the data, and the thread goes, and we just return the reference, so we can use it to match it later. In the implementation of the thread, basically, we just use the data to do our work. In this case, we just sleep for the number of milliseconds. And then we can return we can send a message with whatever we want. Here we just do a tuple with the reference and slept, so the caller knows that we slept. Then we have to remember, of course, we are in C. We can leak everything, so we have to free the environment and free the thread data. And now we can see how the three techniques actually work in the demo. So here we have the first one, so dirty NIF. We just start and we can see that everything works fine. And the first message gets printed, then after 3 seconds, the second one gets printed. Here we have the yielding version, and I will just count. So 1, 2, 3, 4. So if you can see, this is a problem because it didn't sleep actually 3 seconds, because with yielding NIFs, you have to think about the fact that there is always some overhead, because you're doing a little bit of work, then you're doing a bunch of stuff to serialize the state, and then you're resuming the work. So having a precise sleep count is not the perfect use case for this, but you have to consider that when using yield and NIFs. And then for threaded sleep, we have a slightly different spawn, because we have to receive the message, but you can always wrap that in an interface that looks like a synchronous interface. So here too, we can see that we print the first message, and then we wait for 3 seconds, and we print the second one. So everything is good. Let's go on with resources. Okay. Resources are a way to keep long-lived data across NIF calls. They are independently reference counted on both sides. So you basically have a handle on the Elixir side, and another a way to increase and decrease the reference count on the NIF side, which is this one. So when you create a resource, you have the reference count starts from 1, and then you can increase it and decrease it on the C side. And the resource is destroyed when both the Erlang ref count and the NIF ref counts are 0. So you can have something that you can keep on the C side, even if we would get garbage collected on the Elixir side, or vice versa. I will do a quick resource example using a simple shared counter. So we will just have a struct that contains a count amount. And our API will be new counter, which creates a new counter, increment counter, which increments it, and get counter value returns the current counter value. First of all, we have to initialize the resource type, and we're going to do this in the load callback, which is one of the 3 callbacks you can execute during the life cycle of your NIF. So in your NIF init macro, you can pass function pointers to be executed when the NIF is loaded, when it's upgraded, and when it's unloaded. In this case, when it's loaded, we're going to initialize the resource count. This is because resources on the Erlang and Elixir side are just references. If you look at the term, you will just see a reference. But on the C side, each one of these references have a specific resource type. And to do that, we have to create a resource type that is usually put in a global variable because it needs to be accessible when you serialize and deserialize the resource. And you just declare a ErlNIF resource type variable, and then you create a specific resource type by calling the inif open resource type function in the load callback. Note that we are passing a destructor because when resources are destroyed, so when the reference count is 0 from both sides, we can execute some code. This is because the resource might contain some pointers to some externally allocated data, and that is the place where we free them up if we don't want to leak stuff. In this case, we're just allocated the memory for the resource itself, and that is already handled by the beam for us. So we can have an empty destructor here. Now, our API is implemented like this. So first of all, we have the new counter, and we allocate a resource of the specific type that we created before, and that creates the memory space to put our counter into. Then we initialize the count to 0. We call inif release resource because in this case, we just want the resource to be handled on the Elixir side. So we're not keeping it on the C side. We just want it to be garbage collected when the term of the resource has no references on the Elixir side. And then we call inif make resource, which returns a ref, which is going to be passed around and back into our NIF. When we pass back the reference into our NIF, we can basically extract the counters, a pointer to the counter struct from that from argv0, which is the reference that we passed into the NIF. We can increase the count, and we just then return OK. And then we have get counter value, which basically does the same. So it extracts the resource, it extracts the value from the count this time, and it returns the value. So everything is fine, right? So we have a shared counter, we can pass it around. Wrong. So why this is not fine? Let's see. So let's bring back the schedulers to more than 1, and it's a slight foreshadowing here because you can see where this is going. So first, let's try to create a new counter and increment it 5 times and get the counter value. And everything works. It returns 5. Wow, seems to be working. Now let's do a mega counter, and instead of just increasing it in line, we spawn an async task that calls increment counter, and we spawn 100,000 of them. So at the end, we'd expect to see 100,000 here, right? Whoops, it's not. Why? It's not 100,000. This is not a failing demo, by the way. It's just that this line is not atomic because all our processes are accessing the count, and this type of increase is not atomic. So even if it looks like a single instructions, what's happening behind the scenes is that the count is being read from memory, then increased, then wrote back to memory. And if 100,000 processes are doing this together, sometimes we might lose an update. So the key thing here is that you're not in the cozy Erlang concurrency model anymore, and so say hello to race conditions. And how do you solve that? Like you solve race conditions in C. So you have to either use atomics, or you can use some of the primitives that are all offered by the NIF library. So instead of using the the NIF library offers like mutexes, read-write locks, and conditions that are cross-platform, and that also helps you with debugging because they have some names that you can look at when stuff goes wrong. Speaking about stuff that goes wrong, so what do you do? Now, unfortunately, debugging seg faults is not something I can go through in 5 minutes. So this is the part of the talk where I will draw some circles and just tell you debug the rest of the friggin' NIF. And all these tips will be in the code repo too. So again, don't sweat to take photographs. So these are the main tools that we have available. So the most important one is that we are able to compile the emulator in debug mode, which helps a lot because it adds lots of assertions and helpful messages and helpful way to debug the core dumps later. And then for memory problems, you can use address sanitizer or valgrind if you want to be more hardcore about that. And then there is RR, which is record and replay, which is a nice tool from Mozilla, which basically allows you to record what is like something similar to a core dump, but the cool thing is that you can go back in time. So if you crash on a variable that has some garbage in it, you can go see where that variable was written in reverse. So interesting, useful snippets that I found out by like screaming sometimes about this. So because the strange interaction is between like MISA or ASDF and EX and what is documented on the Erlang documentation, which refers to Erlang. So here is how do you build debug emulators. So you just have to pass a flag to KRL as a environment variable, and you can also if you use MISA, you also have to force it to compile the stuff. Otherwise, it just use a precompiled binary, and that's it. How you generate a core dump? So you do uleave-c unlimited, and then you start your EX shell using the debug emulator in this example. Then you crash the thing, and then you can debug your core dump. So you have to point the Earl top variable to a repo, especially if you're using MISA or ASDF, because they clean up the source afterwards. So you have to have a repo with the correct version of OTP you're using, and then you can open up the core dump using the serial script, which the reason you want to do that instead of using the GDB directly is that it provides some niceties. For example, if you have a Earl NIF term in your NIF, you can do ETP and the name of the variable, and it will, instead of a random memory address, it will print the actual value, term value, as you would see it on the Erlang side. To debug memory problems, you can start with ASIN. That's as much as I'm going to tell you. Like you just set a log there, and you tell it to halt on error. So once there is the first fault, it just crashes and prints a lot of very interesting stuff. And then you launch the emulator with the ASIN flavor. And that's it. That's nice stuff, because while preparing the talk, I was able to segfault GDB while trying this out. So have fun. Last section, so choose your poison. This is a quick overview of what languages you can use to write NIFs that are not C. I know you all love C, but you can also use something else. I won't go too much into the pros and cons because it's totally a flavor issue. So with C++, you can use fine, which is it's not my judgment on the language, by the way. So this is a library which is written by Dashbit, and it also powers Python-X. It reduces some NIF boilerplate, and you can use C++ instead of C. I will just show quick examples about on the add, showing the add function that I show in the beginning. This is how the add function looks in Fine. So the nice thing is that your arguments are already deserialized, so they're already a native type. And then on the Elixir side, you have to do some mumbo jumbo, which is the usual stuff, to load the NIF and have a fake NIF implementation that just returns an error, and that's it. With Rust, you can use Rustler. So talk before me, lots of more interesting stuff about that. So you just go quickly. You just have this function. So this is what it looks like in Rust. And you call rustle.init with your Elixir module. And then you do this on the Elixir side, so less boilerplate. And with Zig, you can use Ziegler. And the nice thing about Ziegler is that you can directly write a Zig code inside your Elixir module, and it automatically gets translated into a NIF, and all the like the stubs are created and all that stuff like that. So in the end, this is exactly like macros. So rule number 1, don't write NIFs, and rule number 2, go break rule number 1. Thank you.
Wow. This is the talk I wish I had. I think I made all of those mistakes. Really great job. It's basically lunchtime, so I think if we want, we can do questions in the hallway.
Yeah, sure.
Thank you so much, Riccardo.
Thank you.